Okay, so scatter plots. A scatter plot is a set of data that's graphed as ordered pairs in a coordinate plane. We talked about that a little bit when we were just doing the last one with her daily salary and her commission rate, right? That was some data. When her sales are $100, she was making 58, right? That sort of thing. So there's some data graphed as ordered pairs, but now we're going to graph it. So the independent variable, or the explanatory, as you might hear it, I had to look up how to spell it. Variable is x, and the dependent variable, or the response, is y. Again, think back to Miss Stock and her salary and commission and all that stuff, right? What she makes is dependent on what she sells. Okay. The relationship between any two variables is described using strength, direction, and form. So strength talks about how closely the data is to our mathematical model. Okay, so think about data, it's not perfect, right? If we wanted to talk about height and shoe size, are we going to have the same thing for everybody? Does everybody's foot correlate to their shoe size? Maybe, maybe not, right? Obviously, if you're going to be taller, you're probably going to have a bigger shoe size than if you're a shorty-porty like me and you have inky-dinky feet. Okay? But it's not going to be perfect. Not everybody that is 5'2" wears a size 6 shoe. Okay? Not everybody that's 5'5" wears a whatever size shoe. Does that make sense? So we talk about strength as how good is our data matching to our, how good does our model match our data? Direction refers to whether the line or curve trends upward or downward. Is it positive? As the x variable increases, does the y variable go up? That's a positive relationship. Or does it go downward? Does it have a negative relationship? Meaning the more hours that you work, the less time that you are able to go work out, right? Something like that. So does it have a positive slope or does it have a negative slope? And then form refers to whether the best model for the data is a line or some kind of curve, like an exponential, a logarithmic, a parabola, sinusoidal, all those. Mostly we're dealing with lines in here because this is our line chapter. Okay? When we get next semester to chapter 10 and we're talking about logarithms, those things could be the population of bunny rabbits, right? You got a few bunny rabbits and then all of a sudden, whoosh, you've got 8 million bunny rabbits and they're all having babies. Okay? Something like that. We could talk about it too with our coronavirus. We've got a few people sick and then whoosh, everybody's sick. Does that make sense? So those guys aren't going to be linear. So right now we're just going to be talking about linear data. Okay, so if we look at our examples here using strength, direction, and form, let's describe the relationship between each one of them. So my first picture here, it says the performance on the 100-meter dash and hours doing leg presses in the gym. All right, well here's all these dots are my data and this is my model. It's a line, right? So we know we have a linear data. Would you say that my line strongly represents my data or moderately or not at all? Look at the other ones across it.
Strong.
Yeah, I'd say that's pretty strong, right? The more time I'm doing leg presses in the gym, I'm probably going to be able to run the 100-meter dash better. All right, so this guy is strong. Now, does he have a positive slope or does he have a negative slope? Positive. So I would say this guy is a strong, positive, linear relationship. Okay, look at B. B's data said the population and the number of years after the year 2000 for the small town of Farmville, Colorado. Well, what's happening? As time goes on, are people like, heck yeah, let's move to my small town of Farmville, Colorado? Probably not, right? It's probably losing its appeal to a lot of people. So, would you say that this guy is is it as strong as this guy? No. But it's also not all over the place, so he's not necessarily weak. So I would say this guy's probably like moderately strong. Okay, now is it a positive relationship or a negative relationship? Negative. And is it a line? Yeah. So it's a linear relationship. So a moderately strong negative linear relationship. Ooh, this one's my favorite. Grades and the number of absences in a math class. All right, well, let's look at our data, right? My guess is this guy right here would be my absences. And this guy right here would probably be my grades. So as absences increase, what happens to your grades? They go down, right? Which makes sense. The less time you spend doing math, the worse you're gonna do. So, what do you think about this guy? How could we describe this guy?
Strong negative linear relationship.
Perfect. Strong, negative, linear relationship. Okay, questions on that when we talk about strength, direction, and form. Okay, correlation is almost the same as relationship. And if you do a linear regression, you get a correlation coefficient called R. When we get to our calculators, some of you will see that R value in your calculator, okay? So R is a number between -1 and +1. An R of +1 means that all of the data falls exactly along an upward sloping line. An R of -1 means that the data falls exactly along a negative sloping line. This never really happens except for in bad math class problems, okay? When we make it happen as teachers, then that happens. But let's think about this guy right here. Do all of those data points fall exactly on that line? No. And they never will in the real world. Okay? But this guy closely approximates that data, so we're going to have an R value that's going to be close to +1. This guy is going to have one that's not exactly -1, but he's going to be maybe like -0.5 or something like that. Okay, see how it's a little bit more spread out. The other thing that can happen is if you get an R value equal to 0. There is no relationship at all between the variables. Y doesn't depend on X. In other words, this also never really happens exactly. Okay? There would be no correlation. We're not going to spend a whole lot of time. That's about my whole spiel on correlation. If you want to learn more about correlation, it's a total statistics thing, and you can take AP Stats. Does that make sense? Cool. So these lines right here in our graph, we call our best fit line. Our best fit line is a line that closely approximates the data. Or models the data, if you will. The prediction equation is the equation of that line. Okay, so we just did a whole lesson on writing equations. This is why. Your calculator can also do it for you. That's why you needed a graphing calculator, because we're going to make it do all the hard work for us. Okay? All right, turn the page. I've just given you lots of data. Or lots of vocabulary, if you will. The next page talks about what to be careful with. Okay? Extrapolation. I see this one a lot. So, and when I'm looking at like real world stuff, you should not use your line to make predictions beyond the values of your data's domain. So we talked about the domain being the x's. Meaning, we don't know what's going to happen beyond the data that we have. Okay? When I look back at these guys right here, I'm going to show you my picture. I don't know what's going on beyond here. I could have a data point way up there. So I'm not going to make any predictions out here because I can only predict what's going in here. So extrapolation is taking and saying, okay, well, this is going to be what happens forever. This is bad. Whoop, where are we at? Because you don't really know what's beyond where you've investigated. There's no guarantee that the model remains linear. For example, height versus age, right? It makes sense when we're little kids that your height and your age increase, but you get to a point where you don't keep growing the older you get. And if you're like really old, then you start to shrink a little bit, right? So we can't say that the older you get, the taller you're going to get forever. That would be extrapolation, okay? Interpolation is actually okay. So within the function's domain, so within what the data that we have, the x values that we have, it's okay to use your model and prediction equation to make a prediction. That's considered safe. So if we've investigated the age versus the height of kids from 5 to 15 years old, and we say that they get taller as they get older, and we want to predict the height of somebody that would be 12. That's okay, because we investigated 5 to 15-year-olds. We're not going to say, could we then predict the height of a 35-year-old? Because it won't work. Does that make sense? The last thing that we need to talk about with scatter plots is that correlation doesn't equal causation. Just because they're related doesn't mean it causes it. For example, say you discover a strong correlation between car horsepower and the number of speeding tickets issued by a certain police department. It may appear that horsepower causes speeding, but does it? No. The real cause is, in Mr. McGrath's words, youthful exuberance among males. Right? We just like to go fast when we're young.
Hey, I paid for the whole speedometer and using the whole.
You paid for the whole thing, you're going to use all of it. Oh, look at that. It is youthful exuberance, right? Young males buy fast cars, which then they drive over the speed limit and then they get caught. Or as JT says, he's just using all of the numbers, right? Don't let that 150 feel lonely and not get used. However, the first requirement in finding a true causality is a strong correlation. So correlation may well indicate causation or at least partial causality, okay? So, but it doesn't cause it. Okay. The next two boxes are the steps to use your calculator. Okay, so keep that one handy and we're going to go actually try one. So we're actually going to put some data into our calculator. We're going to make it do all the math in the background and it's going to give us an equation of a prediction equation. Okay? If you don't have a graphing calculator, the bottom box tells you how to do it by hand. Okie dokie. All right. Keep that handy and we're going to refer to it. Let's do an example and I'm going to show you what to put in your calculator and I'm also going to try to show you the steps as we do it. Sound good? All right, so grab your graphing calculator and turn the page. Okay, so it says the table gives the approximate weight in tons and estimates of fuel economy in miles per gallon for several cars. Now, if you notice, they match up. There is this guy in the middle, though, that is missing a value. As you notice, that guy is in the middle of our data. So we're going to do some interpolation instead of an extrapolation. Okay, so we are going to predict down at the bottom once we get everything for that value right there. Okay? All right, so the first thing it says is draw the scatter plot and the line of best fit. All right, so I need to plot my data. My weight are my x's, and my miles per gallon are my y's, which kind of makes sense. Like if you have a lighter car, you're going to be more fuel efficient. Okay, you have a heavier car, it's probably not going to get the best gas mileage. Okay, so at 1.3, I'm at 2.9. There's 1.25, so 1.3, I'm at 29, excuse me. $1.4, I'm at 24. 1.5, I'm at 23. 1.8, there's 1.75, so 1.8, I'm at 21. Skip the 2. 2.1, I'm at 17, there's 2.25, so 2.1. 15, 16, 17. And at 2.4, I'm at 15. All right, now, it says draw a line of best fit. Your calculator, if we had your calculator do all that, it would do all the math in the background, it would run a regression, and it would get up the best fit line for you. What we're going to do is we're going to take our ruler, and we're going to draw the line that closely approximates the data. So touches as many of it as you possibly can. Okay? You can use the edge of your calculator cover, you can use your ID, something like that. So you're going to draw a line that touches as many points as you can. A straight line, okay? So this guy's linear. I'm going to do something kind of like that. You just kind of have to play with it, see where it looks good. So we did part A. We drew the scatter plot and the line of best fit. Now, sometimes the strength, direction, and form is hard to tell when you don't have a lot of data points. Okay? So, part B says describe the relationship between weight and fuel economy in terms of form, direction, and strength. At this point, I don't know if I would call this guy a strong relationship or not because I don't really have a whole lot of data. Does that make sense? So if you're confident saying, that's pretty strong, I'm okay with that. If you're like, I'm not really sure, then you're okay saying moderately strong. Okay? They're also not like all over the place. So this guy I might call moderately strong. What direction is he going? Negative. And what kind of model are we using? What do we draw? A line. So I'm going to say moderately strong, negative, linear relationship. Okay, now's where you have a choice. You can take your line that you've drawn, grab 2 points, and use those data points to write your equation. Or you can use your calculator and it will give you the equation for you. That's what I would suggest you do. So if you look at the box on the previous page, it says steps to use your TI-84 to perform a linear regression. So we're going to look at this one right here. So in my calculator, if I can get you to see both of it, you're going to push the stat button. The stat button is 2 over from the green alpha button. And then you're going to push the 1 edit button. So I need to put my data into my calculator. You should get something that pulls up and looks like this. You should have an L1 and L2, L3, 4, 5, whatever. Step number 2 says put your X values into L1 and you are matching Y values into L2. Remember, it has to have its partner. Those are ordered pairs. So as I put them into my calculator, I'm going to skip the number 2 in my calculator because he doesn't have a match. So the X's are L1s, the Y's are L2s, and that's why I circled it. Now you can put all the L1s in first, all the X's in first by pushing enter. So I'm going to do 1.3, enter. 1.4, enter. 1.5, enter. 1.8, enter. Skip the 2, he doesn't have a partner. 2.1, enter. 2.4, enter. Does anybody have junk in L1 and L2 they need cleaned out? Okay, I'll show you how to do that in a minute if you do. In L2, if you arrow over, remember it has to match. So with the 1.3, I'm going to put 29. 1.4 is 24. 1.5 is 23. 1.8 is 21. Skip the question mark. 2.1, 17. And at 2.4 is 15. You should have the same number of data points in L1 and L2. They should match. If they don't, you've done something wrong. Okay, so I did step 2. I put my X values in L1 and my matching Y values in L2. Go back to the clear screen or the home screen by pushing second quit. So blue and then the mode button. Blue, mode. You should be back to your home screen. That's where you've been doing all your calculations. Now we need to tell the calculator to run a linear regression. So we're going to go back into that stat menu, 2 to the right from the green alpha button, and you're going to arrow over on the top so that calc is highlighted. So arrow to the right to calc. And I want to do a number 4, a lin reg. That stands for a linear regression, and I want it of the form ax plus b. Think about that as mx plus b. So you can push number 4, you can arrow down to number 4, and then you're going to push enter. Some of you will pop up with a screen like this. Some of you, it'll just say LinReg on it, just push enter. If you have an 83, just push enter. Okay? For those of you that have a screen just like mine, we put our X data into L1, we put our Y data into L2. We don't have to worry about frequency list, and we don't have to do all of that stuff, so we can go down here and highlight calculate, so push enter until you get down there, or arrow down and push enter. It's thinking in the background. Okay? Your calculator just did all of the work for you. You now have the equation of your prediction equation. Okay? It should look strikingly similar to mine. They should be close. If you entered in your data a little bit off, it might be off by a little bit, but they should be close. Okay? A is my slope, and B is my y-intercept. So it doesn't quite write it in the nice pretty form. It tells you what A and B are. So A is your slope, B is your y-intercept. So my prediction equation, and we're going to use 3 decimal places, is y equals negative 11.167x plus 41.059. Okay, that's a nice pretty equation, but what does it mean? Like, we have this data here, what does it mean? Okay, let's think about in terms of what x and y are. So let's write it with words instead of x's and y's. So y, remember, is our fuel economy, or miles per gallon. Right? My miles per gallon is negative 11.167 times the weight of the vehicle. Plus 41.059. So you might see it in your homework that says write it in context. This guy is context right there. My miles per gallon is negative 11.167 times the weight of the car plus 41.059. So, part D says predict the fuel economy for a 2-ton car. That's the missing value from the chart. Okay, how could I do that? Yeah, calculator, right? Throw 2 into my equation right there. Okay. Negative 11.16776, times 2 plus 41.059. 18.7. Or in terms of our data, if you look at it, none of them had a decimal, so I would say probably 19 miles per gallon. Let's see if that matches our data and if it fits. So if I look at 2, is it somewhere around 19 from your graph? Yeah, it should be close, right? You should see it somewhere. There's 2. It's about 19. I would say yes. That's good. Okay. Questions so far? So this little box over here on your paper is going to be really handy. Keep that with you as you're working. Okay? In fact, I will probably give you this box when you take your test, so you can have it for reference. Okie dokie? Now, let's just look through this box right here if you're going to do it by hand. So if you don't have a graphing calculator, what would you have done? Well, I would have looked at my graph and I would have said, okay, you can also pick the points that are near your line, but if there's a data point on your line, you can use it. But you're also going to pick 2 points sort of spread out. Okay, you're not picking your first data point and you're not picking your last data point. There was my first data point. Oh, you can't even see it. I'm so sorry. Is that guy even on my line? No, I don't even want to use that point when I'm writing my equation on my line because that guy's not even on it. So you're going to pick 2 points that are near or on your line, and I would say on your line. You would find the slope, draw your line of best fit through the middle of the data of the scatter plot. Do not intentionally connect the dots. We didn't dot to dot it and make it zigzagged, right? Sketch 2 far apart dots on your line. Use the coordinates from those 2 points to calculate the slope. That's what we did in the last section. Calculate the intercept or use your graph to read off the intercept directly. Okay? So then you're going to do the same thing that you did. Calculate your slope, calculate your intercept, and there's your equation. It's a whole lot faster if you just plug your data into your calculator. Okay? Questions? Okay. I'm going to pause this guy.